Hello everyone, welcome back to the channel. In our previous podcast, we explored the forward circulation and learned how the friction pressure affects bottom hole pressure and equivalent circulating density. In this episode, that we are discussing another extremely important well-controlled topic that often surprises the new engineers and well intervention personnel. We have our technical expert with us. He will explain more about the reverse circulation, how the bottom hole pressure and ESD during the workover operation. Over to Hassan.
Now, at first glance, reverse circulation may sound like the exact opposite of forward circulation. And technically, that's true. But from a pressure perspective, reverse circulation can behave very differently. In fact, many people assume that because the same fluid is being circulated at the same rate, the pressure at the bottom of the well should remain the same. But that's not always the case, and understanding why can make the difference between maintaining control of a well and creating a well control problem. So, let's dive in. Let's start with a simple example. Imagine two roads. One is a wide 6-lane highway. The other is a narrow single-lane road. Now imagine that 1,000 vehicles need to travel through each road every hour. Which road will experience more congestion? Obviously, the narrow road, because the same amount of traffic must pass through a much smaller space. The result? More resistance, more delays, more pressure. The exact same principle applies inside a well. Whenever fluid is forced through a smaller flow path, friction pressure increases. And that's the key to understanding reverse circulation. What is reverse circulation? During forward circulation, fluid is pumped down the tubing. Fluid returns through the annulus. During reverse circulation, fluid is pumped down the annulus. Fluid returns through the tubing. The flow direction is completely reversed, and because the flow path changes, the friction pressure changes too. Why does reverse circulation matter? Many workover operations use reverse circulation. Examples include milling operations, fishing jobs, well cleanouts, sand removal, debris circulation, certain well kill operations. As fluids move through different pathways, pressure behavior changes. And if we don't understand those changes, we may underestimate bottom hole pressure. Understanding well geometry. To understand reverse circulation, we first need to understand something called well geometry. In most wells, the inside of the tubing is much smaller than the annulus. Think about it. The annulus is the space between the tubing and the casing. It's often relatively large. The tubing interior, however, is much smaller. This means fluid returning through the tubing encounters more resistance than fluid returning through the annulus, and more resistance means more friction pressure. The garden hose example. Imagine watering your garden. When water flows through a large hose, it moves easily. Now place your thumb over the end of the hose. Suddenly the opening becomes smaller. What happens? The water speeds up. Pressure increases. Resistance increases. This is exactly what happens inside tubing during reverse circulation. The tubing acts like the restricted opening. The fluid must squeeze through a smaller space. As a result, friction pressure increases. Friction pressure changes direction. One of the most important concepts in well control is understanding where friction acts. During forward circulation, annular friction affects bottom hole pressure. During reverse circulation, tubing friction affects bottom hole pressure. This is a critical difference. The pressure acting at the reservoir changes because the location of the friction changes. Downhole tools. Increase friction even more. Now let's make things more interesting. Many workover operations involve downhole tools, such as mills, scrapers, drill bits, junk baskets, wash tools, fishing tools. These tools create restrictions inside the tubing string. Whenever fluid passes through these restrictions, additional friction pressure is created. Think of these tools as speed bumps in the fluid flow path. Every restriction adds resistance. Every resistance adds friction pressure. And every friction pressure increase contributes to bottom hole pressure. This is why engineers must always consider tool friction when performing reverse circulation calculations. Bottom hole pressure. During reverse circulation. When reverse circulating, bottom hole pressure is calculated using hydrostatic pressure, SP equals surface pressure, FPTBG equals tubing friction pressure. Notice something important. Tubing friction is added directly to bottom hole pressure. This means that as tubing friction increases, bottom hole pressure increases. Why reverse circulation often creates higher bottom hole pressure. Here's where many people get surprised. Because tubing is usually smaller than the annulus, tubing friction is often significantly higher than annular friction. And because tubing friction contributes directly to bottom hole pressure during reverse circulation, the bottom hole pressure can become substantially higher than during forward circulation. Same well, same fluid, same depth, same circulation rate, but different pressure, simply because the flow path changed. That's a powerful lesson in well control. Have real-world example. Let's calculate the pressure acting on a reservoir during reverse circulation. Suppose well depth equals 6,000 feet, fluid density equals 12 pp gram brine, surface back pressure equals 350 psi, tubing friction equals 600 psi. Let's determine the bottom hole pressure. Step 1. Calculate hydrostatic pressure using hydrostatic pressure equal 0.52 to fluid density TVD. Hydrostatic pressure 0.052 12 times 6,000. Hydrostatic pressure equals 3744 psi. So now step 2. Calculate bottom hole pressure using GNU Math Block Widget Always Pitch 600 bhp 46694 psi. Therefore, the pressure acting on the perforations is 4,694 psi. What does this tell us? Notice something very important. The fluid density didn't change, the reservoir didn't change, the depth didn't change. The only thing that changed was the circulation path, yet bottom hole pressure increased dramatically. This demonstrates why circulation direction matters. A change in flow path can significantly alter the pressure acting on the formation. Understanding equivalent circulating density, EC. Now let's look at ECD. Remember, ECD stands for equivalent circulating density. It represents the apparent fluid density experienced by the formation while circulating. The fluid itself remains 12 ppg, but because friction pressure adds to bottom hole pressure, the formation experiences a heavier equivalent fluid weight. Check reverse circulation ECD formula. The equation is PTG equals tubing friction pressure, TVD equals true vertical depth, and FD equals fluid density. Calculate the ECD. Substitute the values. Tubing friction equals 600 psi, depth equals 6,000 feet, fluid density equals 12 ppg. ECD equals 600.052 times 6,000 plus 12 ECD equals 600 312 plus 12 ECD equal 0.92 plus 12 ECD equal 13.92 ppg. Therefore, although the actual fluid weight is only 12 ppg, the formation experiences a pressure equivalent to approximately 13.92 ppg while reverse circulating. That's a significant increase. Why ECD matters? If ECD becomes too high, you may fracture the formation, lose circulation, damage the reservoir, reduce well control margins. If ECD becomes too low, you may allow formation fluids into the well, take a kick, increase blowout risk. This is why monitoring ECD is one of the most important responsibilities during circulation operations.
That's great to hear from our technical expert. Now let us summarize today's lesson. Reverse circulation means pumping down the annulus and returning through the tubing. Tubing friction affects bottom hole pressure during the reverse circulation. Smaller tubing create a higher friction pressure. Downhole tool increases friction even further. Bottom hole pressure is often higher during the reverse circulation than during forward circulation. Higher tubing friction result in a higher ECD. Engineers must understand the circulation direction when evaluating well control risk, and perhaps the most important lesson is changing the direction of circulation changes the pressure acting on the reservoir. The fluid may same, the depth may same, the well may be same, but the pressure can be completely different. And in well control, pressure changes everything. Thank you for joining in the today's podcast. If you found this lesson helpful, don't forget to like, share and subscribe to this channel. And let me know in the comment, have you ever seen significant ESD increase during the reverse circulation operation? I love to hear your experience. Stay safe, keep learning and see you in the next episode.